Hey guys, hoping you're having fun with the sub. I just thought I'd stop in to help you a little bit with your lesson that I want you guys to work on today. It's going to lead us into our next chapter, the things we're going to be doing for the next term or so. So what we're going to do is we're just going to talk angles today. We're going to apply it to some stuff that we've learned previous. And for any of you taking the ACT, some of the information we're going to talk about today ends up on the ACT, so that's helpful. We're going to be talking about angles today. Angles of rotation. Our angles that we're going to be focusing on are going to be on the coordinate plane. Okay? So these are our X, Y axes that we're used to seeing. And now we're going to be talking about angles of rotation. The positive x-axis, this is where we're going to base all of our angles off of. This is called the initial side. Initial meaning starting, the original, okay? So we're on the initial side, the positive x-axis, and from here, our angles are going to rotate, okay? So let's say we rotate halfway to the y-axis. This creates a 45-degree angle. So we rotated 45 degrees. This is called the terminating side. This is where our angle terminates, it ends. So we started here at 0, and we rotated to 45 degrees. Terminating side, initial side. So we always rotate counterclockwise, okay? We're rotating backwards. If we were to rotate clockwise, that would actually be a negative angle. So instead, if I were to rotate backwards, like such, okay, this was 90 and another 45. This would be a negative 135-degree angle. We rotated counterclockwise. That's not true. We rotated clockwise. Clockwise is negative. Counterclockwise is positive. Okay? So the negative, we rotate clockwise. And those positive angles, we're rotating counterclockwise. So, some more vocab for this is what we talk about coterminating angles or coterminal angles. For example, if I were to take an angle and it were to rotate all the way around back here, okay? What we did is we just rotated a full 360 plus the 45. This is a 405-degree angle, and it just so happens to end at the same position of a 45. Those are coterminal angles. So a lot of the times when you watch the Olympics, when we're watching skiing or snowboarding videos, happens in ice skating as well, when they're doing rotations. So I'm looking at you now, we can say that that's 0 degrees. If I were to rotate, that's 360 degrees. But if I were to do 2 rotations, so here I'm at 0, I rotate, and I rotate again. That's a 720-degree angle, rotation, right? 2 cycles, but I'm in the same position as 0 and 360. Those are coterminal angles, okay? That's the same right now. I'm looking at you, I'm at 0. If I rotate, that's 180 degrees. I did half a rotation, that's 180. I'm here at 0 again. I rotate. I'm still looking backwards, which was the same as the 180, but I rotated 540 degrees. 1 full rotation and then a half rotation. Coterminal angles. Okay? If we were to build another axis here. Let's say I have this angle, I'll call it 140 degrees. Okay, I rotate this way, and that's 140 degrees. I want to find 2 angles that are coterminal with 140. Okay? An easy one is I can just take my 140 and rotate all the way around again. So I've got my 140 plus a 360. So 140 plus one full cycle, 360. That is also a 500-degree rotation. Okay, so an easy way to find coterminal, add 360. Just rotate one full cycle around. Or another way is that we could rotate backwards. So if I go here and I go all the way around, that's a 360, but I only went 140. So what's left of that angle? So now I'm going to take 360 and I'm going to subtract my 140. That gives me 220 degrees. So this is going to be a negative 220 degree rotation. Okay, I'm rotating back to that 140. That's a negative 220 degrees. Okay, coterminal angles are really important for some of the things that we're going to be doing with moving forward. Pretty basic idea, yeah? Maybe? I don't know. We'll see. Let me know when I get back. All right. So what I've just been showing you here has all been in degrees. We're used to measuring our angles as degrees. We know what a 45 degree is. 90, 180, 360. We know what those mean. But there is a second type of measurement for angles. Just like we have miles versus kilometers, or inches versus centimeters. Okay, they're different types of measurement, but we can get the same measurement. There is another type to measure our angles. Okay, and it is called radians. Okay, so we're going to be talking our radians versus our degrees. I'm going to get us a circle here to help us show that is not centered, but we get the idea. Nope, it's going to bother me. I'll try one more time. Okay. Better. Makes me feel a little bit better. Okay. So what I'm going to do to show you what a radian is. When we're here and I rotate 1 degree, we know what that is. But 1 radian is based off of circles. So in every circle, it has a radius, right? We know that from the center of the circle to an outer point, we create a radius. Well, to measure radians, we can look at the radius of a circle. Okay, so what I'm going to do is I'm going to measure from this point to this point, and I'm going to put a mark on this string to keep track. Okay? All right. So I know you're probably not going to be able to see that point, but it's going to help me measure what I'm looking for. So what we see, I can show you. This is the radius of that circle. All right? So what I'm going to do is I'm going to take this radius and I'm going to measure around the arc of my circle. So I'm going to hit here. There's 1. Well, I'll stop there. I just hit this mark right here. And this is 1 radian. That is 1 radius rotation around the circle. If I do it again, so I'm going to start here at the 1, rotate around. Now I'm looking at 1 more radian. So this is 1 radian, 1 radius rotation around the circle. So at this point, I have 2. 1, 2. Okay, then I'm going to rotate, and my third is going to hit somewhere around here. It's not quite 180, but it's really close. And now I have 1, 2, 3 radians. When I hit this 180 mark, I actually have 3.1415.926 blah, blah, blah radians. Again, 3.14 radians. What's 3.14? Okay, we know that as pi. It takes pi radians, 3.14, to create half a circle. If I were to keep going, I'm going to end up hitting back here at 360, and that's going to give me 2 pi radians. So when we're measuring in radians, we're actually going to be in terms of pi. Halfway around the circle is pi. All the way around the circle is 2 pi radians. Okay, 2 pi radians. When we write degrees, we see 360 with a degree symbol. When we write radians, we don't write radians or show radians. It's in pi, and therefore we know it's a radian. Okay? Halfway around the circle, 180 degrees equals pi. 360 degrees equals 2 pi. 90 degrees equals half of pi, right? Halfway. 270 is 3 pi over 2. You have 1.5 radians, okay? 1.5 pi radians. So what we're going to look at is how do we convert radians into degrees and degrees into radians. It all comes down to this relationship. All right? This conversion process should be a little familiar from chemistry. We're going to use a conversion path to create our radians or our degrees. We'll start off real simple. I'll do 120 degrees. I want to convert 120 degrees into radians. We're in degrees, so I need to somehow cancel out the degrees. So I'm going to multiply by a fraction, and I'm going to put the degrees in the denominator. That way my degrees will reduce out. I want to end up in radians, so I'm going to put pi in the numerator. So I'll end with radians. Okay? And we know the relationship pi equals 180 degrees. So I'm going to put 180 in the denominator. Okay? And all I'm going to do is I'm going to multiply and reduce. So this gives me 120 pi over 180. I'm going to reduce that fraction. They're both divisible by 10, so I'm going to divide by 10. 12 and 18 are both divisible by 6, so that's going to reduce to 2 pi over 3 radians. 120 degrees equals 2 pi over 3 radians. So, if we are converting degrees to radians, we are going to multiply by pi over 180. And we're always going to reduce our fraction, okay? Simplest form. If we go in reverse, I have it in radians, and I want it in degrees. All right? So let's say we have 3 pi over 4 radians. Again, we're going to try to make the conversion. I'm in radians, terms of pi. I want to get rid of the pi. So I put pi in the denominator. That way they'll reduce out. The relationship between pi radians and degrees, pi radians equals 180 degrees. So I'm going to multiply 3 times 180, that is 540 pi over 4 pi. All right, pi divided by pi equals 1, so it's going to reduce out. And 540 over 4, that is going to give me 125. No, 135. There we go. 135 degrees. And that's it. Okay, so if we are converting radians to degrees, what we're going to do is we are going to multiply by 180 over pi. Similar approach, it just depends which is in the numerator and which is in the denominator. Okay? So there is a practice sheet where you're going to be practicing that and see what happens. Okay, the rest of the worksheet has you finding arc length and sector area. So we'll talk about that real quick. Alrighty. So let's look at a circle here. Based off of a circle, we get our radius and we get our central angle here. Arc length and sector area is dependent upon the radius and the arc length, the central angle. What we're looking for is part of a circle. So arc length is this piece along the outside of the circle. It is a part of the total circumference. It's a fraction of the total circumference. So whatever our angle is, that's the fraction of the circle. So we use that angle to find that fraction of the circumference. Our theta is just a variable, also known similar to x and y. Theta is just a Greek letter, and typically when we're dealing with trig or angles, we use Greek letters to notate those unknowns. Our theta is going to be in radians. Okay, so to find the arc length, what we're going to do is we're going to take our theta over 2 pi. That's the fraction of the circle we're looking at, and we're going to multiply it. 2 pi is the full circle, 360. We're going to multiply it by the circumference formula, which is 2 pi r. This is the fraction of the total circumference. But we have a 2 pi in the denominator and a 2 pi in the numerator. Those will reduce to 1, and our arc length formula is theta times radius. So if our angle happened to be pi over 4 and our radius was 7, our arc length would be 7 pi over 4 inches, meters, centimeters, whatever our measurement is. Okay? If it's in degrees, we'd have to come back to the full formula. We couldn't reduce. We would do the same process, but with our degrees. Okay? And sector area. Sector area is this whole instead of looking at the outside of the circle, we're looking at this area of the circle. So instead of circumference, all we do is we look at area of the total circle. So this formula is theta over 2 pi times pi r squared. That's how we find the area of our sector. We have a pi divided by pi, so we could go ahead and reduce that out. And we're looking at the theta over 2 times pi r, no, we reduced pi, times by r squared. All right, so again, if our angle was pi over 4 and we had a radius of 7, I would write this as pi over 4. I'm going to treat this divide by 2 like a 1/2 times 7 squared. There's my theta, my angle in radians, times the 1/2 r squared. So this would give me 49 pi over 8, and we'll say inches squared. Sector area. Okay, if you guys have any more questions, you can go ahead and jump on Khan Academy, check out some of those videos. If any of my math aides have showed up to help you out, ask them some questions. If not, talk to each other, work through this, see how you do. I'll see you guys soon. Bye.